In this video, we'll learn to create and interpret graphs of motion data. Now, this course relies heavily on math skills, and one of the most powerful mathematical tools when relating data to observation is graphing, especially with motion. There are a number of graphing options, but the Cartesian coordinate system, or XY grid, will be our focus for this video. Now, the power of this system is relating two measurements with each other. In it, the convention is to locate X data points using the horizontal axis. Y data points are located using the vertical. The zero value for both axes is where they meet and is referred to as the origin. Now, X values on this grid increase positively to the right and negatively to the left, while the Y values increase positively moving up the axis and negatively moving down. The X variable is usually referred to as the independent variable. When this changes, it causes a change in another measurement. The Y variable is the dependent variable. Changing the X variable has an effect on this measurement. Now, it's important to know that these are conventions rather than rules. And of course, the final graph relies on data points recorded in a table of values as we make our measurements. Again, the convention is to place the cause variable in the left column and the effect variable, or variables, if we want to compare similar results for different measurements, on the right. We would just add other columns further to the right as needed. Now remember that X and Y are just generic labels for our axes. And while it wouldn't be correct to say that time causes changes in these measurements, it is fair to say that unless time changes, we wouldn't be able to see these other things changing. So our convention for motion graphs is to consider the time, our independent variable, and one of the motion measurements, position, velocity, or acceleration, as our dependent. Excel is a friend to scientists and engineers, and generating data for lab reports plays a significant role in this course. So I'll use Excel to demonstrate recording and graphing data. Now, if you recall the linear motion video, we considered a motorized car moving along the floor. Well, we take a different car and decide to measure its motion, and we find that it moves 2.5 meters in each 1 second interval. So we'll record our time and position. In Excel, rather than type all the data, we can use some of its automation to help. I'll just enter the first two data points, and then I'll select these and drag the bottom right corner. Excel will fill the space with data of the same increments. I can do the same with the position data. And once the data is complete, I can create a graph. Now for our XY graph, the best choice is the scatter graph with no line. We'll add the line of best fit or trend line later. Since I've only got one set of data, Excel will generate the plot automatically. I'll adjust the color for the video, and we'll get to work completing the graph. Now a line of best fit is called a trend line in Excel. To add one, just right-click on a data point and select trend line from the pop-up menu. There are a few formatting options, but the main one is the trend type. Since this is linear motion, we'll select linear. We close the dialog box once we're set. Next, let's imagine we have another pair of cars. One with a fresh set of batteries moves uniformly at a rate of 4 meters every second, while the other has an older, weaker battery and moves steadily at 1 meter per second. We can use Excel to record this new data to compare these cars with the first one. Notice we only need new position information. We'll use the same time data for all three plots. Now to add the plots to our graph, we right-click anywhere in the graph and choose Select Data from the pop-up. From here, we're prompted for the data name for the legend, the X values, and we'll choose the time values, and for the Y values, we'll select the values under X2. We'll perform the same steps for the third dataset. And now we'll add the trend lines for the two new datasets. We'll complete the same steps we performed for the first plot, but we'll use different colors to distinguish the plot lines from each other. The video is moving quickly, but the focus here is on what's in the graphs. There are lots of videos online on how to use Excel. Now before we start our analysis of the graphs, just note the full title and axis labels that I expect on every graph. So to start the analysis, recall from math class that in a linear relation plotted in Cartesian coordinates, the rate of the relation is just the slope of the plotted line. And this is found from the ratio of rise to run, where the run is the horizontal distance between 2 points, and the rise is the vertical distance between them. And since time, or t, is our cause variable, the run is our delta, and the position, or x, is our effect variable, making the rise our delta x. And remember, in our last video, we defined this ratio as our velocity, so the slope of our position time graph gives us the velocity over the same time interval. Well, let's do some calculations and see what light the graph can shed on the comparison between results. We'll start with car number 1 and use that rise and run that we drew. Here we rise 5 meters in 2 seconds, and when we calculate the velocity, we get 2.5 meters per second, the same rate of advance for each second of our data. No surprise here, as this is uniform motion. Now before we do the calculations, let's just glance at the graph and see if any insight is readily available. Well, car number 2 with the fresh battery moved quicker and has a higher slope, while the third car with the old battery was slower and has a lower slope. So when you know what to look for, there's some good information on this graph. So we'll complete the calculations. For the second car, if we take a different run of 2 seconds, we get a rise of 8 meters. And calculating the speed here gives a result of 4 meters per second, the higher velocity of car number 2. And finally, for car number 3, still another run of 2 seconds, we rise 2 meters. And calculating this speed, this time we'll calculate the deltas. Our final position was 2 meters, and if we subtract our initial position of 0 meters and do the same with the times of 0 and 2 seconds, we get 2 meters over 2 seconds for a velocity of 1 meter per second, the lower velocity of the third car. So looking at the slope on a plot of position versus time, or a position-time graph, tells us an object's velocity. And for uniform motion, where we consider an object with a velocity that remains constant over time, we have a uniform slope. But this suggests that we can also track velocity versus time, and this would be a velocity-time graph. So plotting the motion of our 3 cars on this type of graph would be 3 different horizontal lines. After all, the value of the velocity is different for each car, but each one was constant. But the picture gets even more interesting when we compare these graphs side by side. Well, we already know what the slope of a position-time graph tells us, but let's look at what we can read besides the velocity from a velocity-time graph. For this, let's look at the area between the velocity of the third car and the time axis. Now this area is a rectangle whose height is the car's velocity, v, and the base is the time interval, delta t. And when we calculate the area, multiplying base by height, we get the product v delta t, or 1 meter per second times 5 seconds. Looking at the units, we multiply and divide by seconds, so this simplifies, leaving a unit of meters, and the result is 5 meters. And looking at the comparison, this is the change in position, or the displacement over the time interval. And considering the algebra, if we start with our velocity formula and rearrange it to isolate displacement, we multiply the right side by delta t and do the same to both sides. And when we clean this up, we see the same relationship. The displacement of an object in uniform motion is the product of its velocity multiplied by the time interval. Now moving up the chart, we see the same is true for the first car and again for car number 3. So now we can read the velocity from a position time graph and displacement from a velocity time graph. Now I know the graphics are racing, but these are precisely the same steps as car number 3. Well, that's linear motion, but how will these graphs look with nonlinear motion? Remember the tennis ball from the last video? We'll enter its data like we did with the cars, and like we did with the car data, let's graph this following the same steps. And we'll format the graph for the video and take a look. Now, instead of a straight line graph, it's a curve, with the position rising for about a quarter second and falling for the same amount of time. But now there's no consistent slope for velocity, so we'll have to review some stuff. Again, looking back to math class, recall that a line that rises to the right has a positive slope, while a line that falls to the right has a negative slope, and a horizontal line has a slope of 0. Now technically, a vertical line has an infinite slope, and physically this can't exist. Now to analyze slope on a graph, we need a straight line. So we'll draw one that touches our plot at one point and runs parallel to the curve at that point. This is called a tangent. This one rises steeply to the right, so the ball's velocity is relatively high here. Now if we add tangents at later times, we see the slope lessens as the ball slows on its way up, is 0 at the top of its flight, and then it becomes negative as it starts to fall and increases steepness negatively as it speeds up on its downward trajectory. So the ball starts quickly upward, slows down and turns around, speeding up as it moves downward. Now if we draw tangents and calculate their slopes starting at the beginning of the trip, and do this several times throughout the trip, we can plot the velocities to create this velocity time graph. Notice the upward speed at the beginning is the same as the downward speed at the end. Now let's compare these two graphs. Since the velocity time curve is based on the slopes, we know slopes of the position time graph line up with the velocity values. So let's look at that area under the velocity time graph. Notice that the first half of the plot is above the time axis since the ball was moving upward, starting at 240 centimeters per second in the positive direction, while the second half is below the time axis as it moves negatively, finishing at 240 centimeters per second. The halfway point occurs at about 0.245 seconds. Unlike the linear motion, these areas are triangles, so the formula is half the height times the base. But our height is our initial velocity, while our base is the time interval for the first half of the flight. If we substitute these with the values from the graph, again paying attention to units, we find the area is 29.4 centimeters. This is awesome because that's how high the ball rises on the position time graph, so it looks like our relationship still works. Now let's take a look at the second area. Since the position time graph is a parabola, the rise time of the ball is the same as the drop time. So the time interval is the same as the first area, but our velocity for this area is the final velocity of negative 240 centimeters per second. If we use these values in our calculation, the result is negative 29.4 centimeters. So the ball falls in the negative direction, the same distance it rose, just as we'd expect. So to sum up, you should have a sense of position time and velocity time graphs and the relationships between their data. There's one more graph we need to complete the picture, the acceleration time graph, but this will have to wait for a few videos.